Are we good to go? Good afternoon, one and all. So, today we are at the third day of the faculty development program. So, here the topic for the day is applications of regression and correlation in business research, which is dealt by Dr. KVS Sharma sir, who is a biostatistician and research coordinator, statistic consultant to SVIMS University at Tirupati. Now, I would like to request Dr. Soumya Sajjan to do the introduction.
Good morning, one and all. I, Dr. Srimati Soumya Sajjan, hereby take the opportunity to introduce today's resource person, Dr. KVS Sharma, retired professor, Department of Statistics, Sri Venkateshwar University, Tirupati. At present, he is rendering his services at the same university as a biostatistician and research coordinator. Sir has completed his master's in statistics in the year 1977 from SV University and training from Indian Statistical Institute, Madras in 1978 and awarded with PhD in statistics in the year 1897 from the SV University. In his 41 years of research experience, Sir has guided 8 MPhils, 20 PhD research scholars with 62 plus publications. Sir has authored 2 books, and in addition to that, he has authored 4 more books in local dialect. His areas of interest stands exclusive, and his major areas of consultations are design and analysis of statistical data, statistical methods in biology and medicine, inventory modeling, SQC, data analysis with Excel, SPSS, multivariate statistical analysis, and many more. With this brief introduction, I would like to hand it over the session to the resource person for further proceedings. Thank you all.
Okay, good afternoon to all of you.
Thank you, ma'am. So I would now request Dr. KVS Sharma sir to share the presentation and begin with the session today.
Okay, thank you, sir. Thank you very much. I'm happy to be on this platform to share some of my ideas on the designated topic for today's session. I'm basically a theoretical statistician. I'm a professor of statistics, basically, as it was mentioned there. Later, after my retirement, the transformation went into a hospital environment. In Tirupati, we have a deemed university-like structure where a lot of research is going on, and I had some interest in that one. So after I worked there for some time, that's what they were reading, biostatistics and this one. And why I'm telling all these things is one may get a doubt why this talk will be useful to us when he is a biostatistician. Statistics, as things stand, basically aims at analyzing data and drawing conclusions. That's the very purpose of looking at statistics. We collect the data, of course. We collect the data and we analyze the data. We carry out the impressions from the data and then interpret. This is classical and good old method of telling what statistics is. For a common man, statistics is basically numbers, what we see in the newspapers rather than text. We are very much interested nowadays to know information rather than data. I will make it a little bit continuous, connecting you from what we observe every day to what is being analyzed in newspapers and all these things. There was a fear among people regarding statistics, and that appears to be even now existing, that statistics is something which is difficult to learn. Unfortunately, it is not correct. In fact, every person from student to a senior man, a layman, an ordinary citizen is a statistician. Knowingly or unknowingly, with an instinct in mind, we try to look back for the history, which is nothing but data. We also connect it to our present situation, that is analysis. We also take decisions, that is interpretation. If we wonder who is not doing all these things, everyone is doing. We see what happened yesterday. We try to correlate with what is to be done now and see what is likely to happen, and we try to predict what is likely to happen in future. This occurs in business, this occurs in administration, this occurs in day-to-day politics, and where not, everywhere. So I don't think anyone is not a statistician. Everyone is a statistician. The only question is whether he is using jargons like correlation, regression, analysis of variance, etc. But everyone does what is called data analysis. And the present audience, I believe that most of the audience are from social sciences and commerce, MBA related. Uh, we are also not an exception. The best statistician known to me, this introduction may be overlapping with what has been told yesterday, day after day, but I am keeping myself safe for a connectivity to my talk today. The best statistician known to me all the time was my mother. Not my mother, your brother's, your friend's mother, everyone's mother. Because probably a lot of statistics comes at home, and mother is known to do even probabilistic arguments with, even though we don't know that she is doing that one. She estimates, she challenges, she verifies whether a challenge is right or not, basing on the evidences that we provide her. She keeps tracks of data on milk vendor, gas availability, provisions availability, how much to cook, whether the item is properly cooked or not. All these things are classical examples of how to say that statistics started at home. Today, we are in a different environment. All that common sense has been conceptually translated into a systematic method of analysis using mathematical and statistical tools. Mathematics played a very comfortable role in the early days during before the 20th, before 19th century itself. There was evidence that statistics was coined. But what is required here is today in 2021, when we are speaking about statistics, it has undergone a lot of metamorphism. A lot of changes have come, just like our corona is taking a lot of variants. Statistics took different places and perhaps occupied or probably dominated the role of the data science people. Data science, statistics, they go together, and everyone who is in business teaching is now supposed to understand what is data science. As a part of data science, a lot of statistics will come. Today, if our students ask us, sir, which type of jobs are possible for us, we simply say business analytics. That is a broad umbrella under which a lot of jobs will come. If it is for research, if somebody asks, sir, what is that I have to do for research, you go for analytics. Analytics means data driven results. Some years ago, maybe some decades before, a PhD thesis was fully with only written text with very few reference to numbers, tables, and graphs. That was the earlier situation, but now we go by data-driven decisions. Your decisions must be supported by the data that has been available with us. Therefore, data plays a prominent role. And today's market also offers data-driven jobs to youngsters, people who are seeking jobs. You get what is known as business analytics, data analyst, let us say visualization expert, systems analyst. There is no hard and fast rule that why should whether somebody can be a data scientist or not. Anyone can be a data scientist provided that you have a strong domain of knowledge in some subject, commerce, management, pure science, mathematics. You take any of them. Now that data science will offer an important area. As a part of data science, we get a lot of statistical tools, and among them, we will be getting what is known as correlation and regression. When I was trying to advise my friends or who asked me on their PhD thesis regarding statistical tools, particularly in social sciences, they were asking me one question normally. Sir, people are nowadays talking about so many techniques like analysis of variance, that test or standardized procedures, this, that, etc. Why don't you check up for the most recent tools and something which looks very interesting and attractive for my thesis? Unfortunately, that is not the correct approach. The type of statistical tools to be used in the research work depends upon the objective of the research. Depending upon the objective, what is that you wish to show, what is that you wish to establish, there exists a tool for that one. That tool may be a recently improved tool or a classical tool. Perhaps a classical tool may be enough to show that particular one. So this is where a lot of testing of hypothesis and other results took place earlier. There were people speaking about saying that, sir, somebody has been using in his thesis, he has used it most of the time as a t-test or some non-parametric test. I want to be very different from that. Why can't I use analysis of variance? Analysis of variance needs a different background for its application. Wherever you apply a t-test, you can't use analysis of variance. So like that, what happens is, instead of being a tool-driven research or technique-driven research, we must look in for objective-driven research, purpose-driven research. In such a research, what happens is, you will be writing the protocol. Protocol means the research plan. You will write the protocol. You say what is your objective, how you are getting the data, what is the methodology you are adopting to analyze the data. Analyze that. I will underline that word analyze because uh, data analysis is important. Excuse 1 second. Sorry. The work from home leads to this type of problems. So these tools are important in the analysis. I will now focus on specifically on what is meant by correlation and what are the types of problems that we are likely to get while looking into the this one. I will share this screen to you. Hope it is visible. I'm sure it must be visible to you. So correlation analysis is what I will speak for some time on correlation analysis and later switch on to regression analysis. We'll look into what exactly we mean by correlation. If somebody asks you while you are walking along a corridor, what is correlation? You simply say it is a characteristic between two variables which measures the relationship. For example, height and weight might be correlated, selling price and volume of sales, they might be correlated, and the researcher will be knowing beforehand, before going to statistics, he will be knowing that they are correlated. Height and weight, yes. The more the height, expected that you will be having more weight also. We call it as correlation. In general, X and Y are said to be correlated if a change in X causes a proportionate change in Y. If X increases, Y also increases. That is what we mean by proportionate change. So we understand the relationship between X and Y with the help of what is known as a scatter diagram or called XY chart. Before we attempt to draw this, the data needs a particular structure. Such a structure is known as paired data. Paired data must be paired. That means first record Y value, X value. Second record Y value, X value. For example, I am the first person, my height, my weight. Second person, my height, his height, his weight. So this should never be scrambled. It must be a pairs only. So this is a plot of these values. When you plot all these values, you are likely to get a relationship curve, and that relationship could be either a linear one or a non-linear one. Linear means like a straight line. I will show that also. And we observe from such figure what is meant by the relationship nature. I will show the picture and then come back. Look at this data. Here is a data having 13 pairs. 13 pairs. First person, X value was 23.5, Y value was 5.7. What is X? What is Y? The researcher will give. There must be some meaning with this X and Y also. If I plot all these things, I am getting this type of diagram. You can see there are dots on this diagram. On these dots, I am showing by mouse, there is apparently some trend. As my X value is increasing from 20 to 32, Y value is also increasing from 5 to 9, more or less in a increasing manner. If not exactly straight line, but it looks like a straight line. This is what is known as the paired data, and it is the scatter diagram. This is an unpaired data. How does the data looks unpaired? This is the unpaired data. In other words, I don't have a data for the second fellow. For the seventh fellow, I don't have the data here. And there is also no reason for me to put it like this. So I can scramble all these things, shuffle them, and we don't plot anything for this type of diagram. When X increases, Y also increase. We call it as a positive relationship, and the diagram may recommend drawing of a straight line like this. When you get like this, we say there is a positive correlation. So correlation must be, first of all, viewed with the help of scatter diagram. There was a claim earlier saying that diagrams are low entities. Why do you draw all these things? Why don't you go look at the numbers and then do? Unfortunately, with reference to correlation analysis, scatter diagram is the vital tool. Like when we go to a doctor for our sugar, he says that you get the test result. The test result is your graph. With the availability of modern computers, you can draw hundreds of these diagrams on one page to understand the nature. Say, for example, 20 variables are there. 20 by 20 table will come indicating the relationship. This type of visual relationship comes like this. This is a situation where when X increases, my Y is decreasing. You see, as X values are increasing by something like I increase the say price, selling price, and people started coming less to me. They are not coming. So price and demand can be possibly like this. So spend more on your advertisements. You are not realizing much profits because you have been unnecessarily spending. Maybe the other way also possible. Here is an example. This is a very common situation that occurs in social sciences. We report a correlation and we'll be sad. We'll be not happy saying that, sir, correlation is very low, sir. I'm not happy. Why it happened? This is the reason. You thought that X and Y either increase or decrease in relation to other, but your data is not showing anything. In this scatter diagram, I am not able to see any type of increasing or decreasing. You can argue anyway. There is no clear relationship like that. Whereas here there is a relationship. There is a relationship here. So here I don't have relationship. Therefore, this is what we call as a zero correlation. Sometimes there may be other relationship, but not correlation. So three broad categories. One is a positive correlation, negative correlation, and zero correlation. You see, there are three variables for me. Instead of drawing one at a time, I draw. This is a medical, the blood related HDL. This is cholesterol, HDL, and LDL. Cholesterol versus cholesterol, there is no correlation. There is no meaning in correlation. So this is only histogram. Cholesterol versus HDL, you see, this is the scatter. Cholesterol versus LDL, this is the scatter. If you look at these two things, you can immediately understand that cholesterol and LDL are more linearly related, but this is a weak linearly, weak. They are not as strong as like this. Like this, we can understand. Today's data analyst, business analytics, they take this type of diagrams and come to a conclusion quickly to understand the nature of relationship among variables. Here is a beautiful situation that occurs in economic and business context. As x increases here, some value, don't bother what is x. As x increases, y is increasing to some extent, becoming more or less flat. After that, it is decreasing. So this type of situation is known as a non-linear correlation. So the first step is we must be very clear by scatter diagram whether it is linear or non-linear. If it is non-linear, what I am going to talk in the remaining slides will not apply. There is a different method of handling this one. What we speak in this session today applies only for linear one, but not this. This is called a curve linear relationship, but most of the real world data often displays like this. Even in business applications, we'll be getting like this. All these diagrams are okay, but every time I can't look at a diagram or I can't comment or compare several relationships using diagrams. So what is required is I need an answer in terms of numbers, numerical measures. Such a numerical measure is given by Pearson's correlation coefficient. For very obvious reasons, let us not bother about the mathematics behind. This is the formula. This formula has different alternative forms to make things convenient for calculation. In those days when there were no computers available, these formulas have been well discussed to see that the calculations are convenient to the user. But later on, nowadays with the help of calculators and computers, all these things is very easy now. And what is required is when you come to calculate, you understand the correlation. It was denoted by Pearson's correlation coefficient, and in the name given for that is R, small r. Small r is for sample, and later we call it as a rho for the population. I will tell about it later. If you have n observations, n pairs of data, I can calculate correlation using this particular one. And what is required is the both x and values must be continuous. What do we mean by continuous? Continuous is a value that is observed on a measurement scale, but not on a counting scale. I hope most of you must be familiar. I need not tell this at this level. Okay. So at this level, I need not work out on this one. Correlation is a strength of linear, R will be calculated and it is required. Oh, I think he was to, yeah. Yeah. So this formula, variables which have been measured on a continuous scale, like height, weight, area, volume, ratios, all these things are continuous. But certain things are discrete. For example, agree, disagree, or low, moderate, high, or those which are on the Likert scale. We call it as a discrete or categorical. And let us all agree today that we don't calculate Pearson's correlation coefficient when the data is on a Likert scale. Strictly speaking, it is not acceptable. With some transformations, it can be done. That is not in the present discussion now. So we shall agree now that all the calculations, all the data must be on a continuous scale. After finding out the correlation coefficient, the value must be between -1 and +1. -1 and +1. So if somebody says that I got correlation is equal to 3.5, simply first say that you check, it is not correct. And it can be -1 or it can up to -1, lowest side -1 and upper side it will be +1. A positive indicates positive value, negative indicates negative value. I will take you to the next one. Am I?
Sir, can you share the PPT? Yeah.
Yeah, I'm sharing, but I'm trying to move on these things. Yeah,
Yeah, yeah.
so correlation has come. Now, I think it must be visible at this level now. A negative value
Yeah, yeah,
indication
exactly. It is visible, sir.
visible, yeah. And when r is equal to plus 1, there we use a word called positive and perfect. Perfect means correlation is equal to 1. No real world problem will show perfect correlation unless the data has been specifically derived for that purpose. For example, when you go for a hotel and if we take some breakfast, one idli is equal to 5 rupees. Two idlis becomes 10 rupees. Three idlis becomes 15 rupees. Now you take a correlation between the number of idlis and the bill, you will get plus 1. So that is a data which has been derived from a formula. But real world problem will not be like that. In fact, even in English, it will not be like this if we take a different context. So this correlation is more or less not, it will be usually close to 1, 0.9, 0.95, 0.8, something like that we call it as positive correlation. Correlation could also be negative. In other words, when more the value, when the more the bargain you do, lesser the payment you are making, we call it as a negative correlation. That can also be negative and it can go up to -1. So larger value indicates stronger relationship. That is the magnitude important, not the sign there. Sign is defined by the domain specialist. Here is an important point on this one. Most of the time, students will be familiar with this. Sir, R must be between -1 plus 1. Closer to 1, it is a good one. But then there is what is called a spurious correlation. Spurious in the sense putting things in a meaningless manner. Say, for example, I was getting data on two variables x and y. You asked me to calculate. I got it. The correlation was 0.9. I was very happy. You are also very happy. And then I asked you, why you got a very good correlation here? Can you tell what is x and y? I don't know, sir. I will refer and tell. When you referred, you found that x is equal to tie length of the student and y is the marks obtained in the examination. So longer the tie student wears, the more will be the marks in the test. That is the meaning you will be getting if you do correlation. Therefore, correlation coefficient should not be calculated unless you are very sure that there is meaning in that correlation. If you feel that there is no meaning, better don't go for correlation. That's the caution that we had to do it. Here is an important information. If the correlation is zero point 0.7 for one person or one context, and in another context it was 0.8, we'll be happy. Yes, 0.8, I got a better correlation than 0.7. Therefore, I will run to conclude something. But instead of taking zero point 0.7, you have to look into another parameter called square of the correlation coefficient. We have to invariably report it in every PhD analysis. Square of a correlation coefficient is known as coefficient of determination. If R is 0.8, its square is 0.8 into 0.8 becomes 0.64. Multiply by 100, you will be getting 64%. That means your correlation tells 64% of the behavior of x by y, behavior of y by x. A very, very important point we have to notice. You can know about x by reading y. You can know about y by reading x, but only 64% you will know. Remaining 36% you cannot understand from the knowledge of correlation. So what is required? We wish that r square must be high. R square will be high if r is very high. Say for example, if r is equal to 0.9, that means 0.9 into 0.9 is 0.81. That means 81% of the relationship is explained by your correlation. Your correlation tells something like that. If I get a correlation of 0.3, 0.3, 0.3 into 0.3 will become very low. Only 9% will be explained. So we expect strong correlations to convey more information. We should see, we are looking at all these things to understand what exactly correlation. Unfortunately, correlation is not to be stopped. We'll see in the next few slides. So 36% is not explained. So it is a correlation coefficient is also an incorrect tool, wrong tool, if the relationship is weak or non-linear. I was showing you a diagram where scatter diagram widely spread data points. In such cases, even if you calculate R, it is of no use. It won't convey much of the things. In many business data circles, or if you are trying going through company reports given in the annual report, if you look such type of data, you will get this type of problem. Correlation in most of the cases will not be that strong. Therefore, interpreting the correlation coefficient must be done with a lot of care. In fact, simply making a Pearson's correlation coefficient and trying to report on that will be a part of the job. It is not the end of the job. So it is important to see that when the scatter diagram shows very high relationship, then only we have to do it. Then only we have to present it like this. So correlation, therefore, comes in this way. Unfortunately, it leaves us with another question. It poses another question. The question is, which is cause, which is effect? We don't know. X and Y are related. Correlation is 0.9. Oh, very good relation, positive relation. It means as X increases, Y is increasing. As Y increases, X is increasing. We stop there. That is what you have done so far. But we didn't answer an interesting thing, whether X is causing changes in Y or Y is causing changes in X. This is called cause and effect. Cause and effect. We in economics we speak about buyer's market and seller's market something. Who is running the show? The market is moved by the buyer. So buyer is the cause, market outcome is the effect. The other way is something else. Market is moving and the buyer is thinking whether to go ahead or not. So market is controlling the buyer or the buyer is controlling the market. On the lighter side, people say somebody was taking a videograph of a puppy on the road. The puppy was wagging the tail. So it is very clear that both the puppy and puppy's body and its tail are wagging, so they are correlated. I can write a comment saying that the dog's tail and dog's body are perfectly correlated, at least with 0.9 relationship, because I am witnessing that one. He got a doubt saying that is the tail wagging the dog or dog wagging the tail? That is what we call cause and effect relationship. Unfortunately, with Pearson's correlation coefficient, you don't answer that question. You only say that is a strong relationship or weak relationship. So correlation has that limitation. Then how to handle that particular one? If there are several variables which are intercorrelated, we can see all possible correlations. These possible correlations and each of them will be the correlation between -1 and +1. If there are 5 variables, will be 10 distinct correlation will be coming there. For example, with 3 variables, we got 3 into 3, 9 table, leave away the diagonal elements, so we will be getting 6. If somebody is using SPSS for their data analysis, you will find all these things as a table. All these correlations can be evaluated with the data analysis part of Excel or any other things like that. I will just illustrate to you with an example because I will spend time on regression enough on that one. Here is a case I will share with you because we must be in a position to apply a tool to any type of situation where there is data. So this is an example in which I have participated in the hospital for which I was working. There was a teacher, there was a faculty doctor. She was interested in finding out whether we can identify newborn babies if they are having underweight. That was her problem. If the baby is born with less than 2.5 kgs, it is said to be a low birth weight. Then they need attention to be admitted in some other care. So she has brought this data for analysis. I don't keep all these things with you. There were 1,000 babies on which they have carried out. They wanted to know whether weight is observable by not measuring the weight, but by measuring the chest circumference or the foot length of the baby. I don't have the machine to weigh the baby, but I can measure the length with a scale or ballpoint pen marking by measuring the foot length or by taking the chest circumference of a newborn baby. The teacher wanted to know from me, sir, are they correlated? That was the first question. What is the correlation between weight of the newborn baby and length of the foot for that baby, and also chest circumference? That was something interesting to me. When I plotted the scatter diagram, you see how interestingly a real life data with a lot of points more or less indicating a straight line pattern. Leave away these trails. It happens in real life data. Certain points will not fall on the line. As foot length is more, the babies are likely to have more weight. Or you can say the other way, more the baby, more the birth weight, more will be the foot length. So we thought that, yeah, probably children having normal birth weight will likely to tend have longer foot, longer feet, longer foot. This was the similar case with reference to chest circumference. They took a tape and measured the chest circumference. Then also, that was the situation for them. When we looked at the correlations, this is what we got. Foot length and foot length. This is an important point. I marked it as red. And also, there is some importance on these diagonal elements. A variable like a foot length or any x is correlated with itself with full correlation. I am correlated to myself, therefore perfectly correlated. I am correlated with myself, perfect. Therefore, correlation is always 1. A certain software will not write anything here. We wrote it as 1. The meaning is there is perfectly correlated. But foot length is correlated with chest circumferences by the tune of 0.9168. That means longer the chest circumferences, more will be the foot length, or longer the foot length, more will be the cc. Similarly, body weight. We have, when you do working on your research projects, you may get a table like this, dots here, or here dots and numbers here. They won't write everything in some software. For example, Excel will not write. Why it is like this? The reason is the correlation between FL and CC is the same as correlation between CC and FL. That means here also it is 0.9168, and the computer will not write it saying that it is unnecessary. There is some specific name for this type of table. We don't look into that one, but this table can be completely understood by looking at into 1, 2, 3. These are the 3 correlations. The same thing would have come here if we write. So in general, when we have bigger problems, say you are studying agricultural output, paddy output in terms of acreage, water resources, rainfall, availability of agriculture labor, etc., etc. You examine a lot of data and try to see the correlation, whether the agricultural output is correlated with that. You will be getting a bigger table, and all these correlations will be listed in it. Therefore, today in the present 2021, in this environment, making a calculation, breaking our head and getting one R value is not any adventure. We must be able to handle a lot of bigger sized problems like this. So this is correlation analysis is an intermediate step in data analysis. I don't say that it is the end of the job. Before that, I will also focus a second on this one. Even though I didn't write all these things, I am sometimes worried that more text will go, but attention must be to listen. If I say that this correlation is 0.9161 between foot length and let us say this one, I will take body weight, easy to understand. Foot length and weight is 0.95. If I say that I got this much of correlation, one of you may raise your hand and say, sir, are you sure? Are you sure? Do you think that it will be always 0.95? You have studied only 1,000 babies, just 1,000 babies. I have got in a similar study somewhere in Delhi where 2,000 babies we have studied, the correlation was only 0.13. Somebody said that in Kerala I studied, I got 0.84. Oh, what is this? You say that correlation different there, different to me, different from somebody else. Yes, it happens. What I'm talking about as correlation and what I spoke all through the previous slides is only a sample correlation. Sample correlation. Correlation coefficient observed, obtained for my sample. But I can't say whether it is always true for the entire population. I don't go into that area now. Population is a bigger one, sample is a smaller one. Your research is always on sample unless you want a population survey. Your article publication will be on sample data. Your real world applications will also be on sample data. And occasionally we go for population observations. So when it is sample, the question will come. That question is in the form of a challenge. Sir, I believe that there will be only a correlation of 0.5 but not 0.95. Somebody raised that question. How do I justify? I have to do what is called a test of hypothesis. That is why in a lot of PhD works and other reports, we find a star somewhere here. Here is a star, here is a star, here may not be a star, etc., etc. I didn't do it because that is not my activity in this particular talk, because that's a testing of hypothesis. But in principle, whether you want it or not, computer software will give you the significance. If you use SPSS, you will be getting a star. What does that star indicate? That star indicates this result could be statistically significant. That means your null hypothesis may be wrong. May be wrong. You may be assuming that the correlation must be 0.5, but I got 0.95. The difference is statistically important. What is meant by statistically important? Statistically significant or important means the finding I got is not an occurrence by chance. It is not by chance. Sometimes we will be getting several results just by chance. No, it is definitely due to a real relationship between X and Y. That is what statistically significant is. So as a part of this, we must check whether it is significant or not. And a low correlation coefficient also doesn't mean that they are uncorrelated. Sometimes I will be getting correlation of 0.2, 0.1. Doesn't say that they are uncorrelated. There may be a curvilinear relationship. When the relationship is not straight line, this Pearson's formula will not work at all. That is not meant for that one. And mere knowledge of correlation doesn't show much. We can at most identify which variables are strongly correlated. Yes, today when we are handling real life problems in what is called business analytics, you may have to handle some 50 to 100 variables at a time. All the 50 variables, when it is done, you can pick up only some of them which are strongly related, either for removal or to inclusion in the study. This is an important factor in what is known as a factor analysis. When we do factor analysis, the first activity to be done is observe the correlations. Similarly, in stepwise regression, when we are working out, we shall see later, we identify those variables which are strongly correlated, and in some cases we remove them, in some cases we invite them. It depends on the requirement. And correlation analysis is, however, a groundwork for running other types of regression and related analysis. So this is one type of activity that we had to work on this one. I will stop this bit and take you to second activity, where I will look at into what is meant by regression analysis. I will minimize this one. I hope this is visible. Yeah. Hope I am able to reach people properly. Correlation, I will, because this is a related activity, I had to tell you. I will minimize this. Yeah. Yes. I'm showing up.
Sir, can you reshare the screen, the
Oh,
presentation? It is
okay,
stopped.
okay. I'll share. Reshare. Visible now? Able
Yes,
to see?
exactly. It is on the first slide.
Yeah. Yes, sir. Open. Can I speak on this one? Yes. Oh, oh. It is again gone. I will put it. Yeah. Can I speak?
Yeah, yeah. It is there, sir.
Yeah. So this is another related aspect. We have seen what is correlation. We came to know how to measure the bondage between variables, how strongly they are correlated, and therefore we shall try to make use of the advantages from correlation. In fact, correlation was not the first slide I should have spoken because I gave the title like that. And in many conventional statistical platforms, we are speaking in terms of correlation and then regression. In fact, it was regression first, then only correlation. One scientist was looking at what is known as biometric analysis. One statistician known as Galton, Sir Francis Galton, he was interested in studying out whether tall fathers are likely to have tall sons or daughters, and short fathers will have short fathers or sons, or short parents mix. What is the average height for them? It is in that context he noticed that irrespective of whether father is tall or mother is tall, the offspring is likely to be somewhere at the average. That word going back to average was first termed as regression. But at that time, one by name Carl Pearson gave a mathematical formulation of that criterion and gave it as correlation analysis. And of course, unfortunately, these two people did not work together. They had their own differences, but both came very useful to the society. And he attended on what is known as regression analysis. Regression in the conventional word means stepping back to average, going back to the average, irrespective of the actual values. But we don't use regression in that sense now. We use regression in the sense of establishing a relationship. Relationship by using a formula. Just like you write a simple interest formula, compound interest formula, growth rate formula. So here also regression analysis leads to give what is meant by a mathematical model or what we call a formula. So it is a functional relationship between a cause and effect situation. It is definitely different from correlation, and it is mainly, it deals with what are known as predictors. I'm talking about this word very specifically because predictor is an important word. We call it as a predictor, a variable as a predictor when it helps in predicting the outcome. I want to know what would be the agricultural outcome for this season, coming season. I have a model. I will substitute rainfall, this, that, etc. When I write all these things into the formula, I will be getting a value. That outcome is your finding, and that's prediction. And all the variables that have been used to calculate that, they are known as predictors. So predictors are those explanatory variables, and in common sense, we call them as independent variables. We call predictors as independent variables and the outcome as dependent variable. For agricultural output is the dependent variable. So we also call it as a response variable, sometimes as output. That is why I was telling at the beginning that a researcher, whether he is a PhD student or a faculty or somebody advising for a company, must have very good clarity on research draft, research proposal. That proposal is known as protocol. Write down the objectives and check whether one of the objectives is prediction of the output or identifying the factors governing the output. If that is the purpose of your study, one of the objectives, then correlation and regression will be useful. If your activity is not to make a relationship model like that, then there is no need for correlation. We need not worry that saying that my correlation is, my research is, thesis is not having regression, etc. Nothing. Depends upon what we wish to communicate. What we wish to communicate. So there shall be a response variable or what is called outcome. So we can think of regression only when there is a response variable and there are some independent predictors. So these predictors will be something like we say, I will go to a bank for a loan or I wish to buy a refrigerator by using Bajaj Finserv or something like that. He will say, sir, your CIBIL score is a little bit low, I can't keep. Why are you talking about my CIBIL score? So he says that CIBIL score is a predictor to know whether you will be a good customer or a bad customer. The words will be unhappy with us. So CIBIL score is a predictor to assess the worthiness of a client, Similarly, average bank balance may determine something. They are the outcomes of interest. Average bank balance, this is not on the outcome of or ARR. Okay, don't worry. Regression, these are also known as predictors. CIBIL score is a predictor. We'll see another example later. And regression helps to build a formula for prediction of outcome by using these predictors. So I will be able to predict, the outcome used in terms of this one. If there is only one predictor, the model is called a simple linear regression. If there are many, we call it as multiple linear regression. So better, I suggest everyone to promote multiple linear regression only because there is no need to spend some time on simple and then go for multiple. When we are able to use a smartphone effectively, why can't we understand a simple regression after learning multiple linear regression? In fact, multiple linear regression is a bigger model compared to simple linear regression. Whatever you do with simple linear regression will not help multilinear, but whatever you do in multiple linear regression will help in simple linear. We call it as partial linear regression later. So we'll take the advice of a statistician if necessary, but MLR, multiple linear regression, is the key for all these things. Now, this is the general formula. Y is equal to A plus B x plus epsilon. This is known as a simple linear regression model. I will say that this Y is the sales and X is the, let us say, amount spent on advertisement. More you spend on advertisement, more you are expecting to turn over. So these things are related with two constants A and B. We don't know what these values are, and these values are to be estimated from data. So regression is a formula you are recommending, but it is evaluated based on the available data with us. And X is known as independent variable or predictor. A and B are constants to be estimated. There is a tool, some of you may be interested. This is known as method of least squares. We don't report anywhere in social sciences, method of least squares. Epsilon denotes a component called random error component. You may not agree with me when I say that there will be a random error. I heard people saying that, sir, I don't have any error in my data. I don't have any error in my tabulation. That's not what we mean here. What we mean here is, in reality, we are likely to get errors. Everyone should accept. If you say that I don't get any error, that it is likely to be wrong. As an example, you take a white paper after going back home. You put your signature 10 times. You don't expect all the 10 to be 100% alike. There will be variations. Now you put the signature again at the 11th time. This fellow will be totally different with all the 10. Why? Same paper, same pen, same technology, same time, but signatures are different. This is what is known as random error component. This random error is something that you can't eliminate. It will be there with us. Only thing is, we try to minimize its impact. That is where statistics and mathematics come. If I remove this epsilon, this becomes curve fitting problem. In some of the earlier commerce books, curve fitting was a chapter. Curve fitting was a chapter. Regression was another chapter. Unfortunately, there was no need. You don't find this type of thing in the recent books, in good books on meant for management and others. You always get regression. So model is A plus Bx plus epsilon. If I have many predictors, x1 is a predictor, x2 is a predictor, there are p predictors for me. We call it as a multiple linear regression. There are p predictors. Again, we use what is known as uh, ordinary least squares regression. So this is not as simple as I am talking in the simple linear regression. Here the calculations are a little bit comfortable. I don't say easy, they are comfortable. Those who can work with correlation can easily work on this one. But here, unfortunately, I don't say this is impossible, but difficult. Difficult. You need a lot of calculation. We call it mathematical matrix theory, inversion of a matrix. All these things are required. And this multiple linear regression happens to be a base model for what today people talk about. If a faculty are present in this meeting, FDP is usually for faculty. Some of your brothers or children might be in software companies. They are analytics companies. They talk about predictive modeling and machine learning. These machine learning models make use of regression. Not this type of regression. We'll look into what exactly it is after some time. So regression makes a core or fundamental thing for day-to-day operations that we are carrying out today. As a result, what happens is regression must be. So I simply say that the relationship is by regression. There are many predictors trying to estimate the output, and the method is known as ordinary least squares, and the computer will help me. Only thing is, I must know that I need a regression problem, and I must also have meaningful data. In other words, all the data between y, x1, x2 refer to one person. For example, when I am talking about another, I have a screen share. I will also share that one. See how I will share one more screen here briefly. I think I can share one more now. Okay, I will give at the end. I have the end of it. Let me not. In Excel, we'll be getting that type of data. In other words, the first person, what is the outcome? What is x1 value? What is x2? What is xp? Second person, what is y? x1, x2, xp. Like that, all the data must be for all the records given like this. So once the data is prepared, we will be able to, what's the number? Something went wrong. Something went wrong here. What's the number? This is known as this one. So here is an illustration. I will try to just get you into the concept of regression. The same problem I took it. Birth weight of babies. I already gave an example. When we calculated, this was the foot length versus birth weight. You see how beautifully it has come. Longer the foot length, more was the weight. And I wrote an equation. This comes easily in Excel. This is what is called a linear regression model. Linear regression model can be easily obtained straight away from Excel. We need not use any advanced software for that one. The model is y is equal to minus 4.25 plus 0.91 x. X is foot length, y is weight, and r square is equal to 0.90. We are trying to understand. Here, you look at first 0.9. 0.90, that means 90.89% of the weight can be explained in terms of foot length. That is a good suggestion for the doctor. We can tell to the doctor, sir, you measure the foot length. I can predict what will be the height. What will be the height? Sir, one second, please. I will join. 1 second, please.
Sure, sir, sure. I hope the session is very interesting for each and everyone attending it. Sir will be back in a moment, so you can just take a quick break of 5 minutes if you wish to. Also, all the presentations will be shared.
So this is the graph we got. 90% of the behavior can be explained in terms of this particular one. ఒక్క నిమిషం నాన్న, ఒక్క నిమిషం ప్లీజ్ వెయిట్ బాబు, ఒక్క నిమిషం, ఒక్క నిమిషం. Yes. Yeah. So foot length appears to be a good marker of birth weight, and R square is 0.908 is high. About 90% of the birth weight can be predicted by foot length, and the equation is given as minus 4.25 plus 0.91 foot length. What I mean to say here is, you measure the foot length, multiply by 0.91, subtract 4.25, you will be getting an estimated value of birth weight. If that way, if you have a machine, that's a different way. If you don't have a weighing machine, this is the method of estimation. That is the purpose of regression. And we call it as a predictive equation. And we get, if suppose foot length is 7, predicted weight becomes 2.12 kg. No, please, don't disturb me. So will this model be true for the population? Is the regression coefficient significant? That is the next question. And that will be done with the help of statistical tests of significance. And we have to answer the following things. Is the prediction correct? Suppose I say that the predicted weight is equal to 2.15. Are you sure? Immediately they will ask, what is the standard error? Whenever we make a prediction, we have to report on what is known as standard error. Standard error is nothing but the standard deviation around the estimated value. How likely you are, how confident you are this way or that. All these things must be reported, sir, in a good research report. We need to test for the significance of the R square value. This is also automatically done by most of the regression packages. A good model shall have high R square, like 0.8, 0.9. If not, the reasons must be investigated. So we must find out why it is. Suppose we have to do it on a real data. We can use a platform like SAS, SPSS, and R. Today, most of the business analytics are going by R, Python, etc. But conventionally, academic researchers use SPSS, Excel, SAS to do all these things. The regression coefficients, their importance must be understood. For example, I don't know statistics, I have a SPSS software with me, I have the problem, I will just attach some of the variables and run. I will be getting an output like this. I must know what I got. Why so many model 1, model 2, model 3, model 4, constant? Sir, I don't know anything about this output. Then run to the statistician, asking him what exactly it is. Okay. So it is important that we must know, if I am using SPSS, I will be getting this type of analysis. You see, the dependent variable is WT, say weight. Independent variables, I will come what is 1, 2, 3, etc. Foot length, head circumference, term, gender, all these things in a different context we have studied. So foot length has a regression coefficient of 0.58, another. These are all the regression coefficients. You see, whether you want it or not, you should report standard error. That is why it will give. Some people say, sir, we will simply close this matter saying that regression coefficient is that's all. And this third column is very, very important. This is called standardized coefficients or beta coefficients. They tell us which variable is more important than others. For example, foot length has 0.61. This magnitude is more when compared to other things. So if you want me to rank them, I'll say first read foot length, then next important is head circumference, then term, then gender. Like this it goes. And it's a t-test automatically. It will be done, and you will also get what is known as statistical significance for that particular one. So like this, what happens here is we will be able to look at what is called known as output from different regression. If I am using SCIS, if I am using R or Python, it will not be like this. It is in a different form. We must be able to understand them basing on the context for which we are working out. Yes, this is exactly a more powerful method. Often we write, sir, let us run stepwise regression. True. What exactly we mean by stepwise regression? In a stepwise regression, a lot of computational exercise will go. It will run with only the most important variable basing on correlation. One regression model will be fitted. Then it will select the next most important variable and run with the two predictors, then with the three predictors, then with the four predictors. Suppose there are 10 times it will run. Every time it will check whether R square is improved or not, whether R square was any R square value has been improving or not. At some stage, if the R square value in the previous model and this model are very close to each other, it will stop. That is the basic idea with stepwise regression. So we'll be in a position to pick up only the most uh, dominant variables, predominant predictors affecting the, instead of handling regression with 25 variables, probably you may end up with only 5 or 6 variables. That is why instead of running ordinary regression, we nowadays suggest go for only stepwise regression. Of course, that is something like an advanced surgery. Therefore, there must be a good doctor to advise you. We can't just pick up things. There are probability in, probability out, selection methods, maximum likelihood, all these things. But stepwise regression is a good method. And it helps screening of variables. I can screen. Do I need all these variables, or shall I? What are the best 4 or 5 variables I'll be able to pick up? So stepwise regression is the most important method of linear regression. So a partial review up to this stage is multiple linear regression deals with several variables at a time. That is to be understood. All the predictors can be included. You can fit the model, identify the regression coefficients, try to interpret. But a better way is try to focus on stepwise regression and try to reduce the number of variables. And basing on that, we can work out the prediction activity with a smaller model. Model will be small. Model will be small and easy to handle. And this method applies to both continuous and categorical predictors. For example, gender, male or female. It is 1, 2 usually we write, or male, female, or 1, 0. Such a variable is known as categorical variable, and regression can be applied for that also. But there will be issues of interpretation. We must know how to interpret that. How to interpret that particular regression, we must be in a position to understand. Apply to categorical variables. In fact, there are developments if you are having, let us say, 3 trichotomous variable, low, moderate, high. Then it is not like gender and it is also not continuous. Then we use a technique known as dummy variable regression. Dummy variable regression, and data entry also is ordinary method, and it will create on its own dummy variables. So this needs some attention for this particular one. Next, we are coming to the end of the job. The road ahead is multiple regression is a basic model, and today, if we have to speak in this year, the current months or current activities now today focus on this. Your youngsters will get jobs if they are good on these methods, predictive models. Other methods include what are known as logistic regression, Poisson regression, Cox regression, and so on. I will just focus outline. I will only speak. I don't have any data to work on this one. Logistic regression, I will explain. It is used when the outcome variable on the y variable has only 2 values, 1 or 0. 1 is yes, 0 is no, whether to sanction low or not to sanction low, whether it is a low birth weight or whether it is a normal birth weight. So if that is the situation, your ordinary least squares multiple regression will not work. We have to go for logistic regression. One of the most highly adopted regression models in predictive business analytics is logistic regression, and it is also parallel method to what is known as discriminant analysis. to discriminate between a good customer and a bad customer. We have applied this model to the low birth weight baby, and we found that foot length is a useful characteristic. We came across one critical value saying that, say, some 6.3 centimeters or so, 7.1 or so. The decision, I asked the doctor how this value will help you. We used what is known as a biomarker analysis using logistic regression. We asked the doctor how this will be useful. She said, sir, in many rural areas, we don't have weighing machines. We can measure the foot length. Based on that, we'll take a decision whether this child needs additional care or she can be maintained as it is. Then how will it help? For foot length, what they suggest is we arrived at, let us say, 7.2 centimeters as the cutoff. Any child whose foot length is more than 7.2, it's a normal. Less than 7.2, then it's critical. Therefore, what they say is they will take a small stick and cut it with 7.2 centimeters, put it in the packet while going to the delivery room. Usually deliveries happen in villages, at home or primary health centers where they may not have the machine. Then immediately after the birth, the nursing sister will put that stick or a ball pen cut at that ball pen refill, cut to 7.2 centimeters, put it at the foot, and then decide whether it is shorter or longer. Then advise, take to the doctor or keep it as it is. So I was a little bit happy at the time when I came to know that logistic regression helped a rural doctor to take a decision like this. Similarly, Poisson regression, many business decision models are based on Poisson. Poisson regression comes when the outcome is categorical, but large number of values are likely to happen, like road accident, traffic misdeeds, and printing errors on documents, all these things. Usually they won't happen, but they can happen up to thousands. Then there is another one, Cox regression, in what is known as business analytics, particularly on insurance companies, where actuarial statistics, they use lot of models from Cox regression. All these things are multivariate statistical models, and predictive analytics makes use of these tools. So these are some of the brief examples I wish to communicate. And before I make a closer signal, I wish to stop this and get you to one Excel statement. I wanted to share this one only to indicate how this practical data will be different from what I am talking in a classroom.
So can you please share the screen again?
Yeah, I am sharing them.
Yeah.
Is it visible? Excel sheet. Are you able to see this Excel sheet?
Yeah. The Excel sheet is on, right?
This data I had downloaded from. I hope I think this is. I have downloaded just for today's lecture, even though I can't. Make useful. This is how real life data occur when somebody is looking at regression. It is not like classroom data. You see here, this was related to lifetime expectations in different countries, studied over different years. Somebody has gathered, and I got it from Kaggle data sets from online sources. In the Afghanistan country, in different years, this was the data available. Life expectancy is 65 in one study, 2014 it is 59 point, etc. They wanted to know what are the most important factors that determine this one. If you look at this data, you may pass it on to SPSS and get regression. But look at the quality of the data. This life expectancy looks a little bit good. But adult mortality, some numbers are very high, some numbers are very low, some numbers are missing, some numbers are zero, some values are too many decimals, some are blanks. All these things will pose new challenges when we want to work out on regression. So regression analysis, when it is to be done, one common requirement everywhere, whether it is a multiple data organization or a research organization, what do we need is quality of the data. Quality of the data, original quality, quality as it is presented, and how it has been given to us. So this needs what is known as pre-processing. Pre-processing means cleaning the data, checking whether all value. For example, some numbers are very high, some numbers are very low. Regression will not object, but your estimates will be having a lot of error, standard error. So we use what is known as transformations. Data must be transformed. There are different methods of transformation, like the normal transformation, z-score transformation, and powerful transformations are there, which are to be done under the guidance of a statistician or with some support in that particular area. So if we look into this type of data, we got so many parameters here. We can fit a regression of life expectancy on, you see here, I think I was reading the variable names. Life expectancy for regressed upon, let us say, the following variables. I will be getting a regression model and probably attempt to interpret these things. Of course, I didn't do that particular one. I will now take back you to my original this one and probably try to get it somewhere. So I was telling logistic, Poisson, and other regressions on this one. This is briefly about how we go for correlation and regression. Regression, I personally feel with a lot of cases that were coming to me, regression analysis is the core, CORE, core of all the modern data science approach.
So the screen is not visible. I just wanted to confirm.
Oh, not visible? I shall. Probably, yeah. I will share it again. The thing is, Zoom was more comfortable to me, but I do not know whether it is. Might be visible now? Not yet. Hope it is visible. So
Yes, sir, it is visible now. Yeah.
But we are coming to the end of the job. Regression is one of the fundamental things, but having got a good result on regression, that is not the end of the job, because it is a model, and that model will not be useful forever. It will be changing immediately after 1 week. This regression model may not be useful. I wish to focus on this point. A model that has been constructed one day may not be useful for all times in future. Therefore, one has to be always updating the models. That is why somebody said all models are wrong. Wrong because they are fundamentally wrong. You have chosen a wrong model, or it was right yesterday, but it is not today. But some models are useful. This is a strong statistics quotation. And we learn only by doing. That's why these people in data science and big data and machine learning models, what they do is they have different computerized mechanisms where data will be coming to them by streaming, STREA, streaming. It is not like our research data where we collect the data and take up the analysis after 3 months. But in real world, what happens is you must be able to fit a regression model and tell the decision as and when the data has come. As and when. 15 minutes ago, there was a change in the business preference of a particular model in Delhi. Now you tell me what shall be my action. So 15 minutes, the data has come, clean, fitted into the model, machine learning adopted, and regression model fitted. This is the decision. Therefore, in such more real-world occasions, as teachers, our job is also to outline the student, tell them that it is going to be your job. In future, you have to update with this one. With the help of computer-oriented technology people, we call data analysts. Therefore, model that has been fitted in a particular context will be changing. We call it as dynamic models that are changing from time to time. But we can't go on doing this like this. We could not do earlier. That's why I say periodical review of a model. Every 3 months, I will improve the model. People were thought. What happens if there was a damage between these 3 months and before 3 months, before the previous review? We don't know. Therefore, in certain environment, particularly in high volume business, like stock market analysis, there will be continuous application of regression modeling. This is how the basic ideas will be done. I will take a couple of seconds to close this shutdown properly. In the sense, correlation was to study the bondage. Regression is to study the relationship. They are not one and the same. You must know whether they are related or not, then only correlation. If you know they are related, what is the nature of relationship and how the predictors explain, that will be done with the help of regression analysis. So regression analysis is the key, and that is the background for the advanced models like factor analysis. In most business, we do factor analysis, principal component analysis, regression, etc. So for all those things, the fundamental requirement will be given with the help of regression. So I am unexpectedly I am having a disturbance. My granddaughter is troubling me. There is some that's why I am not able to spend a lot of time with you. I will take a break at this level and make this open. You can raise issues, and I will be able to share with you my opinions on that one. Thank you very much for listening.
Thank you, sir. Thank you. That was a very great one. So I request all the participants, if you have any queries, kindly put it in the chat box.
Yeah.
Yeah. So we will take a minute's
They can
time,
as well
like
write to
wait
me
for the
through
query.
my email.
Yes, sir.
Yeah, they can also contact on my email given in my first slide,
Yeah.
sms@gmail.com.
Yeah, sure. Yes. So we are really getting good comments here. Very nice, interesting, and informative session by Madhusudan Vyapari sir. So yeah, they're there. Yes, I guess the content was very crisp and clear, and I guess there are no more queries into it. So we could just wait for their queries at your email. And would you be sharing the presentation with them, sir?
Yeah, I will share it to one of you. No, that's better. Or
Yeah,
you
yeah,
can
sure.
take it as it
Yeah.
is.
I will
Either
take the
both.
responsibility
You can take
to.
both. There are two PowerPoints, madam. You can take both.
Sure. Yeah. We'll reach it to them. Sure, sir.
Oh, okay.
Yes.
Fine.
So
Thank
it's
you.
time to thank you, sir. Thank you so much
Yeah.
for sparing
Sorry,
your
I have to leave, but
time.
nice of you. Okay. I'll take leave
Yes.
of you. Okay.
Sure. Thank you. Thank you, sir. All the participants, you are informed that we are in the WhatsApp group, and in the emails, we will be sharing the feedback link. So kindly fill the feedback link to validate yourself for the assessment and also the certification. Thank you. Have a good day.